In this video, we're going to talk about inverse functions. So in order to talk about an inverse function, we have to start with a one-to-one function. A function is called one-to-one if every output corresponds to exactly one input. So for example, the function f at x equals x squared is not one-to-one because we have two different inputs, for example, x equals 2 and x equals negative 2, that can give you the same output. F at 2 is 2 quantity squared is 4, and f at negative 2 is the square of negative 2, negative 2 quantity squared, which is also 4. So that means we have two inputs that give you the same output. Now on the graph, you can see that what that means is we have two different x values that give you the same y value. So in this case, the y value is 4. Of course, there's nothing particularly special about 4. I also have two different inputs that will give me 3 and 2 and 1. That's because all positive real numbers have two square roots, a positive square root and a negative square root. So that means that f at x equals x squared is not a one-to-one function because I can find two inputs that will give me the same output. In order to be a one-to-one function, that can't happen. Each input belongs to one output, but also that one output can only belong to one input. An example of a one-to-one function is the cube function, f at x equals x cubed. This one is one-to-one. Any output y corresponds to exactly one input, which is the cube root of y. So f at y to the 1/3 is y, because each real number has exactly one real cube root. This brings us to something called the horizontal line test. A function f is one-to-one if no horizontal line intersects the graph of f more than once. For example, f at x equals x squared. If we draw a horizontal line at y equals 4, it will pass through both square roots of 4, the positive one and the negative one. So that means that there are two input values that correspond to that output. That is, there are two different x values that correspond to that y value. So that means the function can't be one-to-one. On the other hand, f at x equals x cubed is one-to-one, and if I pick any y value and draw a horizontal line, you can see that it will pass through the curve exactly once, no matter which y value I pick. That's because for each y value, there's exactly one x value. So that means the horizontal line, which selects a y value, corresponds to exactly one x value, which is at the place where it intersects the curve. So this is the x value that corresponds to the y value, and that's the x coordinate. If a function is one-to-one, then it has something called an inverse. The inverse of the function is a rule, which we write as f to the negative 1, that sends each output of f back to its original input. So if we had a domain for a function f, and x was something in that domain, then f is a rule that takes x to some output which we call f at x. The inverse is a function which undoes that. So the inverse f to the negative 1, which we read as the inverse of f or f inverse, it goes back. So it takes this f at x and it takes that back to the original x that it started with. So f is a rule that takes x to some output f at x. But that output for f is now the input for the inverse function, and it takes that input back to the original x value. So f inverse undoes f. Don't be thrown off by this negative 1. F to the negative 1 doesn't mean 1 over f. It's just a way of writing f inverse. It's the thing that undoes f. A function must be one-to-one in order to have an inverse. So let's look at this example here. We have a set of just three numbers. Let's assume that these are the only things in the set, a, b, and c. And we've got some function f, which is a rule that takes everything on this domain into this range over here. So a goes to u, b goes to v, and c also goes to v. So b and c go to the same thing. This isn't a one-to-one function because b and c are two inputs that go to the same output. So how would we define f inverse? F inverse needs to take these u's and v's and go back to the original set of a, b, and c. Well, it's easy to figure out where u would go back to. U would go back to a, but what about v? If we had an inverse, it would have to undo f, so it would have to take v back to its original starting point. However, there are two starting points. Both b and c are starting points that give you v. So should f inverse of b be equal to b, or should it be equal to c? Well, it's impossible to tell, and that's why there's no inverse function, because the function has to tell you where to go. And it can't, because there are two choices. The function f at x equals x squared is not one-to-one. As we commented before, the two inputs x equals 2 and x equals negative 2 both have the same output. F at 2 equals 4 and also f at negative 2 equals 4, which is why it doesn't pass the horizontal line test, because if you draw a horizontal line at 4, it will intersect twice, once when x is negative 2 and once when x is positive 2. If there was an inverse, f inverse, then we would have to have that f inverse of 4 was equal to 2 and f inverse of 4 was also equal to negative 2. But it can't have two values. If one input has two output values, then it's not a function. Remember what a function does. It's a rule. It takes one input and gives you one output. Well, here's an attempt at a rule, but this rule takes one input and it can't decide what output to give you. Should it give you 2 or should it give you negative 2? Well, that's not a very good rule because it doesn't work every time. It doesn't always give you the same output, or it can't decide what output to give you. So that means it's not a function. On the other hand, f at x equals x cubed is a function, and it is one-to-one. F takes x to its cube, x cubed. The inverse of f is the function f inverse, f to the negative 1. You just read that as f inverse, and that takes x cubed back to its cube root. And this is a perfectly well-defined operation with only one output. 1, if that's my input, goes to 1 cubed, which is 1. And then the inverse just goes in the opposite direction. 1 goes back to 1. 2 goes to 2 cubed, which is 8. And then that 8 goes back to its cube root, which is 2. Similarly, 3 goes to its cube 27, but then the inverse takes 27 back to its cube root. Each real number has exactly one real cube root, and so the inverse just takes this number back to its cube root. This works for negative numbers as well, because negative 2 cubed is negative 8, so the cube root of negative 8 is negative 2. And it also works for fractions. 2/3 cubed is 8 over 27, so the inverse takes 8 over 27 back to the cube root, which is 2/3. So we don't normally write a function as f inverse of x cubed. Normally we would write f inverse at x. So we write f inverse of x is the cube root of x. And since each real number has exactly one real cube root, this is a well-defined operation that takes a number to its cube root, so it is a function. This brings us to something called the cancellation laws. We define f inverse so that it undoes f. Remember, that's what we saw with this picture. We start with an x, and then f takes that x to some output, which we call f at x. And then f inverse just undoes that and takes us back to the original x. So F inverse undoes F. So this is one of what we call the cancellation laws. F inverse, evaluated at f at x, takes us back to the original x. It's called a cancellation law because we think of F inverse as canceling with F. F inverse undoes F, and also F undoes F inverse. So that gives you the other cancellation law, which is that if you start with something over here in the range, and you send that back over to something in the domain using F inverse, then F will take you back there. So if we imagine that we have some other point here, which is y, then F inverse will take it over here, which we can call F inverse of y. And then F will take this point back to y. So in the same way that F inverse undoes F, F undoes F inverse, and that gives us the second cancellation law. F at F inverse of y is y. Another way of phrasing the cancellation laws is this. F at x is equal to y is the same as saying that x is equal to F inverse of y. So what this demonstrates is that y is in the domain of F inverse. Y is in the domain of F inverse precisely when y originated in the range of F. So you can see that this y is in the domain of F inverse exactly when y is in the range of F. And similarly, x is in the range of F inverse. X is in the range of F inverse precisely when x was in the domain of F. So another way of writing that is that the domain of F inverse is the same as the range of F, and the range of F inverse is the same as the domain of F. That is to say that the domain and range of F and F inverse switch. So the domain of one is the range of the other, and the range of one is the domain of the other. The domain and range of F and F inverse swap. That's because ultimately what you're doing is you're changing the roles of x and y. You're changing the x's from inputs to outputs and the y's from outputs to inputs. And because of this, there's a certain relationship between the graph of F inverse and the graph of F. In fact, they're the same graph. The graph of F inverse is the same as the graph of F, but with the roles of x and y reversed. So in this picture, here on the left, we see the graph of y equals f at x. Now the horizontal axis here is x, and the vertical axis is y. Now in the other picture, the one on the right, that's not true anymore. Now the x-axis is the vertical axis, and the horizontal axis is y. So this axis, right, the positive x-axis on the left corresponds to the positive vertical axis on the right. And if we just change the color here, the positive vertical axis for the positive y corresponds to the right part of the horizontal axis, as you can see here. So what we actually have is that the graph on the right, which is the graph of the inverse, is the mirror image of the graph on the left, which is the graph of our original function. And that's because what we're doing is we're swapping the roles of x and y. So we just take these positive x values and just swap them with the positive y values, and then we get this picture here. And of course, we swap the negative y values with the negative x values as well. But what that means is that the graph of F inverse is the mirror image of the graph of the original function through a certain axis, and that axis is y equals x, because that's where x and y swap over. So if we want to have the x-axis as the horizontal axis and the y-axis as the vertical axis, then we can graph y equals f inverse of x instead of x equals f inverse of y. So then we have x as the vertical axis, excuse me, x is the horizontal axis, and y is the vertical axis. And you can see that this dashed line in the middle is y equals x. That's our mirror in this picture. So y equals x is our mirror. And the graph of the original function, which you can see here, this is y equals f at x. If you reflect it through the line y equals x, you get the graph y equals f inverse of x, like so. You reflect it through the line y equals x because you're changing the roles of y and x. So the things that were y are now x's, and the things that were x's are now y's. To find a formula for the inverse, we can start with y equals f at x and simply solve for x to get y equals f inverse of y. Now that will give us the inverse as a function of y, which is fine. We may wish, in the end, to write f inverse as a function of x, but we don't have to do that unless we want to. Let's go ahead and find the inverse for this example here. F at x equals x cubed plus y. Let's find the inverse of this function. So we start by writing y equals x cubed plus 5. And basically we just want to solve for x. So the first thing we do is subtract 5 from both sides, and then we take the cube root. So y minus 5 to the 1/3 is equal to x. Now this function right here is f inverse of y. That is to say, the cube root of y minus 5 is the formula that gives you the inverse. So our inverse, f inverse of y, is equal to y minus 5 quantity raised to the 1/3. That's our inverse as a function of y. If we want f inverse as a function of x, we simply swap all of our y's with x's. So we replace y with x. So then f inverse of x is equal to the cube root of x minus 5, or x minus 5 quantity raised to the 1/3 power. The only reason that you would necessarily want to rewrite your function as a function of x is if you wanted to graph f and f inverse on the same axes, the same xy axes in the same plane. If you just want it as a formula, then this is fine. What does the formula say? It says take some value, y, that's your input, and then from that input you subtract 5, and then whatever the result is, you take it to the 1/3 power. So you start with some input, you subtract 5 from it, and take it to the 1/3 power. Now if I put an x here, the rule is the same. We take some input, we subtract 5 from that input, and then whatever the answer is, we take the 1/3 power. So the rule is the same, it's just we've changed the label, we've changed the name, but the rule is the same. You take an input, subtract 5, and then cube root it. You take an input, you subtract 5 from it, and then cube root the result. It's the same either way. Let's do another example. Here we have g at x is equal to the square root of x minus 3. So we do it the same way. You start with y equals the square root, or the radical, of x minus 3. And our goal is to solve for x in terms of y. So we square both sides. So y squared is the square of the square root, so that's just going to be x minus 3. And then we add 3 to both sides. So y squared plus 3 is equal to x. And everything that is equal to x, that gives you the formula for the inverse. So in this case, it's the inverse of g. So g inverse of y. So g inverse of y is equal to y squared plus 3. And again, if we want g inverse as a function of x, then all we have to do is just replace all of the y's with x's. So g inverse of x is equal to x squared plus 3. And again, it's the same formula, you're just replacing the variable. So you have an input of y, and your output is determined by taking that input, you square the input, and then you add 3. That hasn't changed here. Your input is x. You take that input and square it, and then add 3. So square the input, add 3, square the input, add 3. It's the same function, just in terms of a different variable. Let's do another one. Find a formula for the inverse of h at x equals 2x plus 1 quantity divided by x plus 2. So how do we do this? Well, we're going to do it in the same way. You start with y equals h at x, which in this case is 2x plus 1 divided by x plus 2. And again, you want to solve for x in terms of y. So the first thing that we do is we multiply both sides by x plus 2. That's equal to 2x plus 1. So we're going to write this as x times y plus 2y is equal to 2x plus 1. We want to solve for x, so we're trying to get all of the x's together. So xy minus 2x is equal to 1 minus 2y. So notice I've also subtracted that 2y over to the other side. So now I factor out the x times y minus 2 is equal to 1 minus 2y. So x is equal to 1 minus 2y divided by y minus 2. Divided by y minus 2. And again, whatever x is equal to, that's the formula for the inverse. So in this case, we're looking at h inverse of y. So h inverse of y is equal to 1 minus 2y divided by y minus 2. And as usual, if you want h inverse as a function of x, you simply just swap all of the y's out with x's. So h inverse of x is equal to 1 minus 2x divided by x minus 2. And as I mentioned before, the main reason that you'd want to do that is so that you can graph h inverse on the xy plane with x as the horizontal axis and y as the vertical axis. So for purposes of graphing, you'd probably want it to be in terms of x, but if you just want a formula, you can leave it in terms of y. It might not be obvious that this function h even has an inverse. However, looking at the graph, you can easily see that it satisfies the horizontal line test. That is to say that if you draw any horizontal line, it will intersect at most once. Of course, there is one line that doesn't intersect at all, and that's the horizontal asymptote, which is at x equals 2. So that's about right here at x equals 2. There we are. Maybe we'll just move that up just a little bit. There we go. So that's a horizontal asymptote, and that doesn't intersect the curve at all. But any other vertical line will intersect exactly once. Let's talk a little bit about restricting the domain. In example 2, we saw that the inverse of g at x equals the square root of x minus 3 is given by g inverse at x equals x squared plus 3. Now this might look like a problem because g inverse doesn't look like it's one-to-one, and it isn't one-to-one if you look at the entire real line from negative infinity to infinity, because the graph of this function, the graph y equals x squared plus 3, is a parabola. However, the domain of g inverse is not the entire real line from minus infinity to positive infinity. Remember that the domain of g inverse is the range of g. Well, here's a graph of g. G at x equals the square root of x minus 3. The range of g is the set of all non-negative real numbers. That is, all of the numbers from 0 to infinity. So that's the range of g. well, then the domain of G inverse is the same. So the domain of G inverse is the set from 0 to infinity, including 0. That is, the set of non-negative real numbers. And if you look at the graph of G inverse of x on just the set from 0 to infinity, including 0, then it is in fact 1 to 1, because it's just one half, one branch of the parabola. If you put them on the same xy plane, or on the same xy axes, then the graph of y equals g inverse of x is the reflection of the graph of y equals g of x through the line y equals x. So this is the line y equals x. And down here, this is y equals g at x, there. Remember that g at x is the square root of x minus 3. So it's the square root function shifted over by 3 units. That's just the top half of a parabola which is opening up to the right. Now if you reflect that through the line y equals x, you're going to get just one half of a parabola opening up, and that's what you get here. So this is y equals g inverse of x, which is x cubed plus 3. Not x cubed, x squared plus 3. So you can see that it's not the entire parabola, it's just half of the parabola. And G inverse is 1 to 1 if you're just looking at that half, the right half of the parabola. Let's look at some important examples of inverse functions. Specifically, we're going to look at the inverse trigonometric functions. We'll start with the inverse of sine. Well, sine is not a one-to-one function. In fact, it's periodic, so for every output, there are an infinite number of inputs. So that means we have to restrict the domain, and that's what we do. So we restrict the domain to an interval where the function is 1 to 1. And in this case, the case of sine, we restrict our function to the domain from minus pi over 2 to positive pi over 2, which is basically that little bit right there. So on the graph, it's this part of the graph. So what you can see is that on this interval from minus pi over 2 to positive pi over 2, you get all of the possible outputs for sine. You start at minus 1, and then you slowly work your way up to positive 1. And you get all of these values, and these are the only values you can get as an output for sine. You get all of these values, and you get them just once on the interval from minus pi over 2 to positive pi over 2. So this is our restricted domain for sine. And on this restricted domain, your function sine is 1 to 1, so it has an inverse. The inverse of sine is called inverse sine, or it's also called arc sine. Those names are both considered acceptable. So here we're looking at the graph of both sine and inverse sine. So we see that the restricted domain for sine, that's this blue dashed curve here, the restricted domain is from minus pi over 2 to positive pi over 2. So that's this. This is all you get of sine. And on this interval, it is 1 to 1, so it has an inverse, which we call inverse sine or arc sine, and it's the reflection of the graph of sine x through the line y equals x. And so that gives you this solid curve right here, which is y equals inverse sine of x. The domain of inverse sine of x is minus 1 to 1. That's because that's the range of sine. So the range of sine becomes the domain of sine inverse. And the domain of sine becomes the range of sine inverse. So the range of sine inverse is minus pi over 2 to positive pi over 2, because that is the restricted domain of sine. We can do the same sort of thing with cosine. So the function g at x equals cosine of x, of course, is not one-to-one, it's periodic. So again, we need to restrict the domain to a portion where it is one-to-one. And we restrict it to the domain 0 to pi. So that gives you just this bit of the graph right here. So the restricted domain is from 0 to pi. Again, we achieve all of the output values of cosine. We start up here with 1, and then we work our way down to -1, which is down here. So you get all of the output values for cosine, and you get them exactly once. So on this restricted interval from 0 to pi, your function cosine is 1-to-1, so it has an inverse, and it's called the inverse cosine or the arc cosine. Here you can see their graphs. This dashed line is cosine. You can see that it's 1-to-1 on this interval. And so its inverse has a graph given by reflecting the graph of cosine through the line y equals x, and that gives you this graph, which is the graph of inverse cosine. The domain of the inverse cosine is -1-to-1. As you can see in the graph, -1-to-1. Of course, this is the range of cosine, so the range of cosine is the domain of inverse cosine. And the restricted domain of cosine becomes the range of inverse cosine. So the range is from 0 to pi. So you can see that along your y-axis, the range for the solid curve, the smallest value is 0, and the largest value when x is equal to -1 is pi. We can also talk about the inverse of tangent. So tangent is also periodic. In fact, it's periodic with period pi, not even 2 pi. So it's not 1-to-1 on its full domain. So again, we have to restrict the domain. And in this case, we restrict it to -pi/2 to +pi/2. Now notice that this is an open interval. We can't include the endpoints. So that's this interval right here, -pi/2 to +pi/2. So that's this interval. But of course we can't include the endpoints because tangent is not defined at the endpoints. Tangent is not defined at -pi/2 or +pi/2. Those are vertical asymptotes. So let's just graph our function here on the restricted domain. So this is a 1-to-1 function on this restricted domain, so it has an inverse, and that inverse is called inverse tangent or arctangent. Here you can see the graph of tangent on its restricted domain and the inverse tangent. So again, tangent is this blue dashed curve, at least on its restricted domain between -pi/2 and +pi/2. And the graph of its inverse is obtained by reflecting through the line y equals x. And so that gives us this solid black curve here, which is the inverse tangent. Now, notice some important features are the asymptotes. So tangent has a vertical asymptote at -pi/2 and +pi/2. Those also get reflected. So inverse tangent has horizontal asymptotes at -pi/2 and +pi/2. Now this one down here is -pi/2. The horizontal line is sort of covering up the minus sign, but there's a minus there, -pi/2. So the vertical asymptotes of tangent become horizontal asymptotes for inverse tangent. Here we go. This is a graph of just the inverse tangent. You can see that its domain is all real numbers from -infinity to infinity. That's because the range of tangent is the set of all real numbers, so the domain of inverse tangent is the same as the range of tangent. So the range of tangent is all real numbers, so the domain of inverse tangent is all real numbers. Now our restricted domain for tangent is minus pi over 2 to positive pi over 2. So that's the range of inverse tangent. The range of inverse tangent is the same as the domain of tangent, which is restricted. It's restricted to minus pi over 2 to positive pi over 2. And you can see that in the picture. The range, that's all of the y values, goes from minus pi over 2 to positive pi over 2, not including those endpoints, because those are asymptotic values. Let's do a little bit of computation. Let's compute the inverse sine of square root of 3 over 2. So how does this work? Well, this is going to be equal to some angle, which we can call theta. So what we're trying to figure out is what theta is it such that sine of theta is equal to the square root of 3 over 2? And the simple answer is that there's a lot of them because sine is periodic. Well, how are we gonna figure this out? Well, let's draw a circle and let's give it some axes here. Now what we're interested in is so this is the unit circle, and we're interested in where the y value is square root of 3 over 2, because remember sine is the y value. So where's that going to be? Well, one such value is right here at when theta is pi over 3. So when theta is pi over 3, that gives you the point with coordinates 1/2 and square root of 3 over 2. So that's one such place where the y value is square root of 3 over 2, but that's not the only one. In fact, we can just look at a reflection over here, and this point also has y coordinate square root of 3 over 2. In this case, the x coordinate is minus 1/2 square root of 3 over 2. And this angle is 2 pi over 3. That's this angle there. So there are two values of theta, two angles where the y coordinate is square root of 3 over 2, but in fact there are infinitely many because I could just keep going around the circle as many times as I want. Now, we're only interested in one because we're looking at the inverse of sine. The inverse of sine is the inverse for a restricted domain of sine. Remember, the domain of sine has been restricted, and it was restricted to minus pi over 2 to positive pi over 2. That means we're only looking for angles that will land you on the right side of the circle. So we're thinking now of this angle as minus pi over 2, and this top angle is pi over 2. So we're over here now. We're only looking at angles between minus pi over 2 and positive pi over 2. So what does that mean? That means we're interested in this point right here. So this is the point we're interested in. So the angle in particular that we're interested in is pi over 3. So in that case, theta is equal to pi over 3. So sine inverse of square root of 3 over 2 is pi over 3. Let's do another example, but for inverse cosine. Okay, so let's do the same thing. This is going to give us some angle theta. So cosine of theta is equal to minus pi, not minus pi, cosine of theta is equal to minus 1 over 2. So now this is the x coordinate on the unit circle. So let's just draw a unit circle like so, and we'll draw in some axes here like that. And again, we're interested now in the x coordinate. Now the x coordinate is minus 1/2. So that means we're going to go out here to minus 1/2. So that gives us either this point or this point down here. So the one down here is minus 1/2 comma minus square root of 3 over 2. And this point on top is minus 1/2 positive square root of 3 over 2. So we want to figure out which one of these points we're interested in, because we want to figure out the angle that gives them. Well, this angle right here, this is our 2 pi over 3, 2 pi over 3, and this angle down here, this one is, well, if this is 2 pi over 3, then this is 3 pi over 3. and this one's 4 pi over 3. So what does that mean? That means that if your angle is 2 pi over 3, you have an x-coordinate of minus 1/2. If your theta is 4 pi over 3, you get an x-coordinate of minus 1/2. So these are possible theta values. But of course there are infinitely many because we can just keep going around the circle. We can go around the circle as many times as we want in either direction. But again, we're not interested in all possible thetas. We're only interested in one. We're looking at cosine theta on a restricted domain. Remember, the restricted domain for cosine is 0 to pi. So that's the top half of the circle here. So this is 0, and 3 pi over 3, that's the same thing as pi. So we're looking at the top half of the circle. So we're only interested in angles that can land you on the top half of the circle. And if you're just looking between 0 and pi, there's only one angle that does that, and that's 2 pi over 3. So 2 pi over 3. So theta equals 2 pi over 3. So that means that the inverse of cosine, evaluated at minus 1/2, is 2 pi over 3. Okay, what about this? Cosine inverse of sine of pi over 6. Well, it will help us to just evaluate what sine of pi over 6 is. So again, let's draw our unit circle. Maybe this one's a little bit bigger than before. And then we'll just draw our x and y axes, like so. Okay, so sine of pi over 6, that means we're looking at this angle here, that's pi over 6. And that gives us coordinates where x is square root of 3 over 2, and y is 1/2. So since theta is pi over 6, that means it's lower down on the circle, so that means the x value is larger. So the larger value is square root of 3 over 2, so that's x, and the smaller value is 1/2. Okay, so what we're looking for here is sine of pi over 6, so that's the y-coordinate. So that means we're looking at the y-coordinate, which is 1/2. So 1/2. So that means that cosine inverse of sine of pi over 6 is equal to cosine inverse of 1/2. Now, cosine inverse of 1/2 is going to give us an angle, and it's the angle where the x-coordinate is 1/2. Because now this is going to give us some angle theta, and cosine of theta is 1/2. So we started off by looking at where the y-coordinate was 1/2, but now this is the x-coordinate, so we're interested in where the x-coordinate is 1/2. So that's where the x-coordinate is 1/2 is right here. So where the x-coordinate is 1/2, that's up here. That's this point. So that's where x is 1/2 and y is the square root of 3 over 2. So now we're interested in this coordinate. Let's just change the color here. So we're interested in that coordinate. Now this is pi over 3. So that tells us that theta is pi over 3. So pi over 6, you're looking at the y-coordinate for pi over 6, that's 1/2. But then you're looking at cosine inverse of 1/2. So that means you want to know what the x-coordinate is, where the x-coordinate is 1/2. And the x-coordinate is 1/2 when theta is pi over 3. So that tells us that cosine inverse of sine of pi over 6 is equal to cosine inverse of 1/2 is equal to pi over 3. And that's your answer. Okay, well, let's look at another example. Sine inverse of sine of 9 pi over 4. Now you might be tempted at first to say, oh, well, I can use a cancellation law here. We're looking at sine inverse of sine, so don't those two cancel? Well, yes and no. the answer is not going to be 9 pi over 4, because remember that sine inverse is the inverse of sine on a restricted domain, and 9 pi over 4 is outside of that restricted domain. Let's just draw our unit circle here. And let's draw in some axes, like so. So where is 9 pi over 4? Well, this right here, that's 1 pi over 4, and then we have 2 pi over 4, and then this one right here would be 3 pi over 4, and then 4 pi over 4 is pi, and then we have 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4 is 2 pi, of course. And so then 9 pi over 4 is, we're back over here. So 9 pi over 4 has reference angle pi over 4. These two are what we say coterminal, because they start at 0 and they both end along the same radius, which is here. So pi over 4 and 9 pi over 4 are what we say coterminal. So what does that mean? That means sine of 9 pi over 4 is the same as sine of 1 pi over 4. So sine inverse of sine 9 pi over 4 is equal to sine inverse of sine of pi over 4. Now pi over 4 is inside the restricted domain, so remember that the restricted domain is here. That's our restricted domain, between minus pi over 2 and positive pi over 2. Now pi over 4 is in there, so that tells us that we can use the cancellation laws. So this is just going to be pi over 4. Now if you prefer, you can just compute it. Sine of pi over 4, that's the square root of 2 over 2. And then you have sine inverse of square root of 2 over 2, but that's of course pi over 4. So if you don't want to use the cancellation law, you can actually just evaluate it directly. But you can use the cancellation law only because pi over 4 is inside the restricted domain. It's very important when you're using the cancellation laws to make sure you're in the right domain. 9 pi over 4 is outside of that restricted domain. It's too big. We've gone all the way around the circle. So that means we just look at the coterminal angle, which is inside that interval, inside that restricted domain. So this leads us to this little remark here. The inverse trigonometric functions are only inverses of the trigonometric functions on restricted domains. So sine inverse sine of x is x, but only when x is between minus pi over 2 and positive pi over 2, including the endpoints. Cosine inverse of cosine of x is x, but only when x is between 0 and pi, including the endpoints. Tangent inverse of tangent x is x, but only, again, if x is between minus pi over 2 and positive pi over 2. Although in this case, we can't include the endpoints because tangent of x is not defined there. Let's do another example. In this case, let's evaluate cosine of the inverse of sine evaluated at 3/5. So how do you go about solving a problem like this? Well, basically, the idea is that this sine inverse of 3/5 is going to be some angle. So theta is an angle, which is the inverse sine of 3/5. So that means that sine of theta is equal to 3/5. Well, once you know what sine is, you can work out what cosine is using the Pythagorean identity, because we know that cosine of theta squared plus sine of theta squared is equal to 1. Okay, but we know what sine of theta is. So cosine theta squared plus sine of theta, which is 3/5, squared is equal to 1. So that means cosine of theta squared plus 9 over 25 is equal to 1. So subtract the 9 over 25, you get cosine theta squared is equal to 1 minus 9 over 25, which is 16 over 25. So cosine of theta is equal to plus or minus the square root of 16 over 25, which is plus or minus 4 over 5. Plus or minus. So we have to figure out what quadrant we're in. Is this going to be a plus or a minus? Well, how do we figure that out? Well, we just have to think about our restricted domain for sine, because sine inverse is the inverse of sine on a restricted domain. So let's just draw our unit circle like we usually do. When in doubt, draw a unit circle. And what do we know here? Well, sine inverse of 3/5 is going to give you an angle between minus pi over 2 and positive pi over 2. So that means it's going to be over here somewhere. But that means you're on the right side of the circle. And if you're on the right side of the circle, then the x-coordinate is positive. So anywhere on the right side of the circle, you'll have that cosine of theta is greater than or equal to 0. So that means that you're looking at the positive value. So it's going to be positive. So cosine of theta is the positive square root. So it's positive 4 over 5. Another way to think about this is in terms of right triangles. What do we know? We know that sine of theta is the opposite over the hypotenuse in a certain right triangle. So we could actually draw that right triangle. So here's a right triangle, like so. And this is a right triangle. And what do we know about it? Well, sine of theta is 3 over 5. So that means the opposite side is 3. So if this is theta, then that means that this is 3, and the hypotenuse is 5. So that means that this side is a. Well, we can figure out what that is using the Pythagorean theorem. So a squared plus 3 squared is equal to the hypotenuse squared, 5 squared. So a squared plus 9 is equal to 25. So a squared is equal to 25 minus 9, which is 16. So a is equal to the square root of 16, which is 4. So that means that a is equal to 4. Now these numbers should look familiar because 25 minus 9, that's 1 here. In this computation, 1 is 25 over 25. So this is 25 over 25 minus 9 over 25. That's where that 16 comes from. So, and then you compute the square root and you get the 4. Now that's sine of theta is 3/5. So using that information, we're able to figure out what this length right here is, and it's 4. But cosine of theta is adjacent over hypotenuse. And we just worked out that the adjacent side is 4 over the hypotenuse is 5. So you get 4/5 that way as well. So you get the same thing either way. Let's do another example. So in this case, we want to evaluate tangent of the inverse cosine of 2/3. So we're going to approach this the same way. So this inverse cosine is going to give you an angle, and we want to figure out what tangent of that angle is. So we know that cosine of theta is equal to 2 over 3. And our goal is to figure out what tangent of theta is. That's our goal. Well, once you know cosine, you can work out what the other trigonometric functions are, although there's a little question about whether you have a positive or a negative. So let's figure all this out. So we know that cosine of theta is 2/3. Let's figure out what sine is. Well, again, we can use the Pythagorean identity. Cosine of theta squared plus sine of theta squared is equal to 1. But we know what cosine of theta is. So 2/3 squared plus sine of theta squared is equal to 1. So 4/9 plus sine of theta squared is equal to 1. Sine of theta squared is equal to 1 minus 4 over 9, which is 9 over 9 minus 4 over 9, so that's 5/9. So that tells us that sine of theta is plus or minus the square root of 5 over 9, which is plus or minus the square root of 5 over 3. So we're faced with the same problem that we had before. We have a plus or minus and we need to figure out whether it's plus or minus. And that, again, depends on where you are on the xy plane. And we can figure that out again by looking at the fact that we're looking at cosine but on a restricted domain. So cosine inverse is the inverse of cosine but on a restricted domain. So that restricted domain is between 0 and pi. So we'll draw a unit circle like so, and we'll put in some axes like this. And we're interested in the restricted domain of cosine. The restricted domain for cosine is from 0 to pi, so that means it's the top half of the circle. Now, when you're on the top half of the circle, that means that the y-coordinates are positive, so that means anywhere on the top half of the circle, sine of theta is going to be positive, or greater than or equal to 0. So that means you want the positive square root. So sine of theta is the positive square root of 5 over 3. So now we have cosine and sine. The thing we want is tangent, but of course tangent is sine over cosine. So we write that tangent of theta is sine of theta over cosine of theta, which is the square root of 5 over 3 divided by cosine, which was 2/3. So that gives us square root of 5 over 2. And that's your answer. Now, once again, we can view this in terms of a right triangle. So let's construct a right triangle, like so. So let's say that this is our right triangle here, and this is our angle theta. Now, what do we know? We know that cosine of theta is adjacent over hypotenuse. But we also know that it's 2 over 3. So that means if we construct our right triangle, so the adjacent side is 2, and the hypotenuse is 3, then this will be our triangle. So we just have to determine what tangent is. Well, tangent of theta is opposite over adjacent. So we just need to figure out what this opposite side is. We need to complete the triangle. So this can be b, for example. Well, using the Pythagorean theorem, we have that 2 squared plus b squared is equal to 3 squared. So 4 plus b squared is equal to 9. So b squared is equal to 9 minus 4, which of course is 5. So b is equal to the square root of 5. So this is the square root of 5. So tangent is the opposite over adjacent, so it's the square root of 5 over 2, which of course is the same thing. So either way you do it, you'll get the same thing.